Welcome back. In this video, we'll continue to learn about nuclear chemistry. Specifically, we'll learn about the different units that are used to measure ionizing radiation. This includes measuring the rates of radioactive decay, measuring how much energy gets absorbed per kilogram, and then also how to measure the effect that radiation has on our bodies. We'll also then perform some calculations using the half-life of isotopes to determine how much radioactivity exists after a set period of time, or how much sample there was to begin with. There are three classifications or three categories of units involving radiation. Some units are used to measure the activity of the source. Those are the becquerel and the curie. The becquerel is equivalent to 1 radioactive decay per second, and the curie is equal to 3.7 times 10 to the 10 becquerels, or 37 billion decays per second. And what this is doing is measuring the number of times that a radioactive event occurs per second. The absorbed dose has two different types of units. The SI unit is the gray, that is equivalent to 1 joule of energy absorbed per kilogram. And the radiation absorbed dose, the rad, is equivalent to 1/100th of a gray. So 1 gray equals 100 rad. Finally, we have the biological effective dose. The sievert is the SI unit, the standard unit for this. This is also looking at energy absorbed per kilogram. And then the Röntgen equivalent for man, or the rem, is related to the sievert. 1 sievert is 100 rem. And what that looks at is how the radiation is actually affecting our biological processes. Let's take a look more at the rem in detail. So if you have received radiation doses, or over time, the amount of radiation you experience increases. At a level between 0 and 25 rem, there's nothing really noticeable that occurs. Between about 25 and 50 rem, then we can start to have some measurable effects. However, these are temporary and they are slight. From about 100 to 200 rem, this is when we start to see some really difficult effects to deal with. You start getting visibly ill, nauseous, your white blood cell count decreases very drastically. And then as we go up more and more, you have more detrimental effects. A dose of 500 or more rem has been seen to cause death in over half the people exposed to that dose within approximately a month after that exposure. So we're talking about very, very high levels of radiation at that point. So you might be wondering, how much radiation are you exposed to? It turns out, if you are an average US citizen or person here in the United States, not a whole lot. So looking at the scale here, you can see that this is measured in millirem per year. And so within a year, you're getting about 230 millirem from radon. If you're living in Denver, you have a higher level of radon or radiation from the sun than you do if you're living at lower elevation. So if you add together all of these sources from naturally occurring sources, you get somewhere in the 300 or so, 400 or so milligram per year. Looking at man-made sources, medical procedures accounts for the largest amount, and clearly the amount of radiation you get from those depends on how many medical procedures you undergo that use radiation. And so you could get anywhere between 300, 350, maybe 400 milligram a year. So we're looking at somewhere around 600, 700 millirem per year. And you need 25 rem in order to start seeing any kind of noticeable effect. So it takes decades of normal buildup of radiation to have it even start to affect you at all. So for the average person, radiation exposure is not really an issue. It only becomes an issue if you are in a work environment or a living environment where you have extremely high levels of radiation. This includes working in dental offices, working in different medical centers where they perform radiation treatments, and typically where you are the person performing the procedure. And so they take extra precautions to make sure that those people reduce their exposure and that we keep track of the effect that this can have on your body. Let's now turn our attention to half-lives. So the radioactive decay process is a random process. We cannot actually predict at what point a given atom is going to undergo nuclear decay. But what we can do is reliably measure and report radioactive decay for large samples. And since a given mass of sample, if you have 10, 100, 200 grams of a sample, you've got literally trillions upon trillions of particles. Even having that small amount makes it a reliable measurement to determine at what point they collectively will be decaying. So the half-life is a numerical value, and it's the time that it takes for half of the atoms of a substance to undergo radioactive decay. We can quantify this by this equation here, where the final amount, either in mass or in radioactive activity, is equal to the initial mass or radioactive levels times 1/2 raised to an exponent, where the value of that exponent is the number of half-lives that it has been decaying. So if we were to graph the amount of particles remaining, amount of radioactive particles remaining after, as a function of half-lives, what we see is that after one half-life, we've lost half of the sample. After another half-life, that same amount of time, we've lost half of what was left over. So now we're only at 1/4 of the initial amount. You go one more half-life, and now we're at 1/8 of the initial amount. One more half-life, and we're at 1/16 of the initial amount. And so you can see it decays more slowly as we go over time. The activity, the radioactive levels decrease more each time that it decays. And that's because we have lower amounts of sample that are actually decaying. All right, let's try a couple calculations here. I will walk you through this one, and then I want you to try the next two on your own beforehand. So if we have a typical smoke detector, which contains about 0.5 micrograms of americium, and the decay process of americium-241 has a half-life of 432.2 years. How much americium would remain if in the smoke detector after 25 years? All right, so what do we have here? We have an initial amount, 0.5 micrograms. We have the time that it takes for it to undergo one half-life, 432.2 years, and we're told how long it has been since the detector was put into work. So we know this initial amount. We're trying to find the final amount. We need to know the actual number of half-lives, which we don't have. So what we need to do is calculate the number of half-lives. We know that if we had spent 432.2 years, that would be one half-life. But what about if it's only 25 years? What we do is we use this ratio of the half-life in order to find out the number of half-lives. So we have spent 25 years. So we take our 25 years and we multiply by the ratio involving the number of years and the half-life, such that the years cancel and we're left solving for numbers of half-lives. So we can't leave this ratio as it is. We need to invert it. When we invert, we see that our years will cancel. Like so. And then we are left with the number of half-lives. So we have about a 20th of a half-life. To then find the actual final mass, we set the initial amount, we multiply by 1/2 and raise to the power to an exponent equal to the number of half-lives. We simplify and solve, and we get that the final amount after 25 years is 0.48 micrograms. This number seems reasonable because while 25 years does seem like a long time, when we compare it to the half-life, or the amount of time it would have taken for half of it to decay, it's not very long. So we wouldn't expect much of it to have decayed away. All right, here is another problem. I'd like for you to try this one on your own and see if you can figure it out. Welcome back. So in this problem, we have sulfur 35. It's a radioactive isotope, and the half-life of this isotope is 87.5 days. A researcher purchases a sample of sulfur 35, which has an initial activity of 25 millicurie. We want to know what's the activity of the sample after 350 days. So again, we want to find a final amount here. The main difference between this problem and the last one is that instead of dealing with a mass of a radioisotope, we're dealing with the activity. But mass and activity are going to be essentially synonymous for us, and so we can use them interchangeably. So as before, we don't know the number of half-lives. We need to solve for that. So we can take the ratio involving the half-lives. We know that one half-life is 87.5 days. We can rearrange that and multiply by the time that we actually spent, which was 350 days. So we multiply by the ratio inverted, so our days cancel, and we're left with the number of half-lives, which is 4. To then find the final activity, we multiply the initial activity, 25 millicurie, times 1/2 raised to the 4th power. This gets us a value of 1.6 millicurie. And this makes sense that this is much lower than the initial sample activity because we've gone multiple half-lives. All right, here's one last problem. Go ahead, pause the video and see if you can figure this one out, and then come back and I'll walk you through it. Welcome back. So here we have carbon-14. This is an isotope that can be used in what's called carbon dating. It allows us to estimate the age of different organic material after it has died. So we take a sample of dead tissue and it contains 22.3 picograms of carbon-14. We know the sample was 17,100 years old. How much of the carbon-14 was present in the tissue when that tissue died? So what happens here is we know the half-life, we know how old the sample is, so we can find the number of half-lives from that information, and we have a final amount of carbon-14, so we need to find the initial amount. So we're looking for the initial amount, we have the final amount. Right away, hopefully you should be able to recognize that answer choices A and B are invalid. The reason is because we can't have started with a lower amount of sample than what we started with. So we know A and B are bad choices because they would assert that we started with a lower amount of sample. To find the number of half-lives, we take the ratio between years and half-lives, and we multiply that ratio by the length of time that we spent in such a way that the number of years cancels out. We're left with the number of half-lives. So this was 3 half-lives long. We can then start using the equation. We know that the final amount is 22.3 picograms. The initial amount is unknown, so let's just call that mass M. We multiply that by 1/2 raised to the 3rd power. We can then simplify that and rearrange by dividing both sides by 0.125, and we can solve for the mass. That's equal to 178 picograms. And that's our answer. So that's it for this video. Thanks for watching. Have a great day.